Some friends in Illinois wanted me to work on this one, so hi friends in Illinois. And they wanted me to talk about the difference between the Hicks income and substitution effect and the Slutsky income and substitution effect. Now these are both related to the Slutsky equation, which breaks apart the total change in demand for a product due to a price change into the income and the substitution effect. Now, the Slutsky equation, though, is involving calculus, so it involves infinitesimal changes in prices and infinitesimal changes in income. So whenever you want to talk about illustrating the Slutsky equation with a particular change in price that is a discrete change of like $1 change in price, not an infinitesimal change, you have to choose how you want to approximate or demonstrate sort of what the Slutsky equation is saying for this discrete change. So that's why there are various ways that you can go about doing this. So in order to do this as quickly as I can and focus on the income and substitution effects, I'm going to use a very simple utility function, just utility equals x times y, and we're going to start with a simple budget of $6, and the price of x and the price of y are $1. And what we want to do is illustrate in these two different ways the way that Sir John Hicks wanted us to look at it, the way that made sense to him, and compare that to the way Yevgeny Slutsky, the inventor of the Slutsky equation, thought was the best way to illustrate these two. And they're both interesting. I wouldn't say that one is better or worse than the other. It's just they show you slightly different things, and you need to understand the differences. Also, what we're going to do as part of this is we're going to talk about the compensating and equivalent variation. And then at the end, if we haven't fallen over yet, we're going to talk about how this a little bit relates to the difference in calculating a price index when prices change. So I'll briefly mention the Laspeyres and the Paasche price indexes. But let's dive in here. We want to determine the Hicks income substitution effect and the Slutsky income and substitution effect, and we're going to determine the compensating and equivalent variations. I have on this handout that you can download at the link in the video below. I encourage you to go ahead and do that and print it out so that you can do this along with me. And of course, down here, we have printout of some indifference curves, and we have two different sets of indifference curves here. They're the same, but we're going to use one of them to illustrate the Hicks method and one to illustrate the Slutsky method. Now here I have a set of steps that one might go through in order to solve all of these problems. Just kind of a brief rundown of how to think about what you need to do in this situation. No matter what you're doing, we need to start with number one, and we need to solve the original utility maximization problem and determine how much x, how much y this person would buy to maximize their utility, given their income, given the prices, and determine their utility. There are a couple of ways we could go about doing this. Now, if we knew what the Marshallian or Walrasian demand functions are, in this case, we know they would be to split the budget equally between the two goods, because the utility function is x times y, so x's and y's are basically treated equally here, and the exponents are the same on x and y, and the prices are the same. So what's going to happen is they're going to split their budget in two, since the prices are the same, consume the same amount. Now, if we didn't know this, we'd set up a utility maximization problem. And so let's run through that extremely quickly here. So we could set up Lagrangians, but I'm going to use the quicker method, setting the marginal rate of substitution, and use the shortcut formula for marginal rate of substitution for a Cobb-Douglas. And I'll link to my video about that if you're not familiar with that shortcut. But the marginal rate of substitution for this utility function is just going to be y over x. And we set that equal to the ratio of the prices. So this is our first equation. The slope of an indifference curve, marginal rate of substitution, will be y over x. And we set that equal to the ratio of the prices, which is the slope of the budget line. And that's just 1 over 1, which is just 1. So that's going to give us that y equals x, as I was talking about. Now, our second equation here is we assumed that we started with $6. And so $6 is the budget. And that has to be equal to the price of X, 1, times how many X you buy, plus 1, the price of Y, times how many Y you buy. And since Y equals X, we can just substitute in for one or the other. We'll say Y equals X here. And so we have $6 equals 2X. X is going to equal to 3 units, and Y is also going to be equal to 3 because Y equals X. And the amount of utility we're going to get here, we just plug back into that utility function, X times Y, and we get 3 times 3 is 9. Now, let's solve for the final utility maximization problem after the price of Y increases to $2. So we set up the same kind of problem here. First equation, marginal rate of substitution is Y over X. Set that equal to the ratio of the price of X divided by the price of Y. Now it's 1 over 2, or 1/2. And so now when we solve that for Y or X, we just get Y equals 1/2 X. They're going to buy half as much Y as they do X now because the price of Y went up to $2. So I'll call this the final consumption basket. So we plug that into our budget line equation, which is they still have $6. That equals $1 for each X plus $2 for each Y. We substitute 1/2 X here in for Y, and we get that $6 equals 1X plus 2 times 1/2 X. Well, that's just 1X again. And so we get that X is going to be equal to 3 as before, and Y is going to equal 1/2 X. So Y is going to equal 1.5 units. And this is typical of what you always see when you do a Cobb-Douglas utility function. When the price of one good changes, the consumption of the other good stays the same. So X stays 3 units, but the amount of Y gets cut in half because its price doubled. So the Cobb-Douglas utility function, you allocate your budget towards buying X and Y, and you spend a fixed part of your budget on X and Y depending on your utility function, and the prices are what determine how much you buy. Yevgeny Slutsky, when he wanted to illustrate his equation that breaks changes in purchasing into the income and substitution effects for a discrete change in price like this, from $1 to $2 for the price of Y, Slutsky said, okay, in order to get rid of the income effect, let's just give this person enough money so that they could buy their old basket at the new prices. And so Slutsky said, find the budget. How much would it cost to buy the old basket at the new prices? So the old basket was when they were buying 3 Ys and 3 X's, and the new prices here are $1 and $2. What amount of money would the person need to buy that? And so the answer is just, well, we need $1 to buy each X, so it would be $1 times 3 for the original amount of X, plus we need $2 for each of those original 3 Ys. And so what we would need is 3 plus 6 is $9. Oh, I forgot. Let's go ahead and calculate the utility here for our final basket, just so we have that there. Our utility would be 3 times 1.5 equals 4.5 utils. So we see that the person's utility went down after the price went up. If, as Slutsky suggested, in order to illustrate getting rid of the income effect of a price change, we just give the person the budget they would need to go back to the old basket if they wanted to, then we'd have to give them $9. But here's the thing. If we give the person $9, they're not going to buy the same basket that they used to. They're not going to buy 3 X's and 3 Y's. So what this is going to allow the person to do is get to a higher indifference curve, get to a higher utility level. So what we want to do here is calculate the budget, which we did, and then we need to optimize their utility given this hypothetical budget that would allow them to get back to the same purchasing power as before, buy the same basket, but at the new prices, what would the person actually buy? So what would the person buy with the new budget that literally removes the income effect at the new prices? So we set up our problem and we say, okay, well, our first equation is going to be marginal rate of substitution, y over x equals, we're using the new prices, so 1/2. And of course we solve that and we get the same thing we did before, y equals 1/2 x. And then we need to plug that into this new budget equation with the higher budget. We have $9 now. We can spend that $1 for each x plus $2 for each y. And so we plug that in here for y, and we get $9 equals x plus 2 times 1/2 x. Of course, we get the same kind of math that we had up here, except we have a higher budget. So we're going to get 9 equals 2x, or x equals 4.5 units, and then y is going to be half as many x, so half of 4.5, 2.25 units. Now, how much utility is the person going to get in this case? Well, if we plug that into our utility function, u equals x, well, they're going to be able to buy 4.5 units of x times 2.25 units of y. This person's going to end up with 10.125 utils. So we are, in a way, getting rid of the income effect because they have the same purchasing power as they did before when we give them $9. However, this is going to give the person a higher utility. They're going to feel better off. They're going to feel wealthier than they did before. Instead of 9 utils, we're giving them 10.125 utils at that budget. So the Slutsky decomposition, let's graph what we have here for these 3 results and talk about what that decomposition is going to look like. So let's go down here to our difference curve map. This is where we'll do Slutsky. And our original budget was $6. And so the price of x and the price of y were 1. So our original budget line is going to go from, we could buy 6 y's or 6 x's or any combination in between. And so our original solution was 3 x's and 3 y's. So let's call that point A there. And then after the price went up, the price of y doubled. So we could only afford 3 y's if we spent all our money on y. We could still afford 6 x's if we want to. So we have this new blue budget line, and our optimal utility is here at B. And we can see our utility went down. We can see the total change in the quantity of y is here from A to B, right? 1.5 units. So if we wanted to make a little diagram here of the total change, originally we were buying 3 units of y, and that was at point A. And then in the end, we were buying at point B, we were buying 1.5 units of y. So that's the total effect of the price change. But our solution here says that if we gave the person enough money to get rid of the income effect, then they would buy 2.25 units of y. And so let's graph this third budget line. The third budget line is going to have $9 as the budget and the new prices, $1 and $2. And we're going to graph this hypothetical consumption basket of 4.5 x's and 2.25 y's. So with this hypothetical solution, in the Slutsky decomposition, this person could afford 9 x's at $1 with $9. They could afford 4.5 y's at $2 each with $9. And we connect those points to make the budget line. And we see that the green budget line is parallel to the blue one, meaning that the only difference between the green and the blue is an income change. So this is a way to remember what the income effect is. It's always the difference between the 2 budget lines that are parallel, because a parallel shift in a budget line is an income change. Now, what we've done here between the red and the green is we have rotated. We have twisted through point A. And this is the Slutsky approach, is to keep the budget line going through point A, meaning we could afford point A with either budget line, the green or the red, but we're twisting, rotating through point A, which means we're going to end up at a different point. And the point that we figured out was 4.5 x's, 2.25 y's. And we see this green point is at 4.5 x's and between 2 and 2.5 y's, so that's 2.25. So this is point C. This is the hypothetical Slutsky decomposition. And so again, if we look at that total change from A to B, that's the 1.5 difference right here. What the hypothetical decomposition basket using Slutsky's method here does is allow us to put a point somewhere between those to break it into the income and substitution effects. Now in this case, this point, this hypothetical point C, happens to be exactly, precisely halfway in between points A and B. This is not necessary, it's not required, and it's not normally going to be the case that the decomposition basket is exactly halfway in between these. In this case, it just happens to be because of the numbers and because of the utility function that we chose. And so what we would say is this distance between A and C, because what we're doing between A and C is we're rotating. We're changing the opportunity cost between the two goods, X and Y. We're changing the amount of X you have to give up in order to obtain another Y. That's the substitution effect. So when you're twisting, that's the substitution effect. When you're shifting parallel, because that's what you do when you give someone more or less income, between B and C is the income effect. So here, that's the income effect. And so we would calculate those two. 3.3 minus 2.25 is the substitution effect, and they happen to be the same magnitude in this case. 0.75 for the substitution effect and 0.75 for the income effect, the total effect being the sum of the two, 0.75 plus 0.75. Now, this is different from the way I normally do income and substitution effects. I usually use Professor Hicks's approach. So let's see what changes when we do that. So for the Hicks decomposition, the only difference is instead of the hypothetical basket, as in the Slutsky method being, let's give the person enough money to literally remove the effect of the price change on their income. Let's give them enough money to where they would have the same purchasing power and they could buy their old basket. Sir John Hicks said, well, it makes more sense to me to illustrate it this way. Instead of keeping their purchasing power exactly the same where they could afford the old basket, let's keep their utility constant. So this comes into the idea of a Hicksian demand function. A Hicksian or compensated demand function compensates people not in a way where they could buy their old basket, but in a way that it keeps their utility constant. That's what we mean when we say a Hicksian demand or a compensated demand. So for Hicks, we have to solve a different problem. And Hicks said, let's get them back to their old utility level at the new prices in the cheapest way. And so we have an optimization problem that we have to solve. We set up an optimization problem to get them back to the old utility at the new prices. And we ask, what would this person buy with whatever budget it is that removes the pain, removes the utility change from the price increase in this case. So let's set up that problem and solve it. So our first equation, marginal rate of substitution, y over x, equals the ratio of the new prices here. So the ratio of the new prices is that 1/2. And then the second equation guarantees that they get the old utility level. We don't know the budget, so we can't use a budget equation as the second equation. We know the utility we want them to get. We want to get them back to that old utility level of 9 here. And so our utility function is x times y. And we want to ensure that that equals 9 when we're done. And so those are the two equations we're going to use. So again, just like we've done a couple of times in the past, we don't have to redo our efforts every single time. We know that y equals 1/2 x when we're looking at the new prices. We plug that in here for y. And so we're going to have x to the first power times 1/2 x to the first power equals 9. And if you're wondering why I'm writing the first power there, it's just because if it wasn't the first power, this is where I see a lot of people make mistakes doing this kind of problem. What you want to do with whatever power this is on y, you want to distribute it both to the 1/2 and to the x. I know it doesn't matter in this case since the power is to the first power, but so we'd have x to the first power times 1/2 to the first power times x to the first power equals 9. And I know we wouldn't have to do all that, but what if it was to the 0.3 power? I just want to make sure you're aware that you have to keep track of those powers. Here we're going to have x squared, but 1/2 to the first power. So 1/2 x squared equals 9, which gives us x squared equals 18. So x is the square root of 18, which gives us about 4.243 or so. And then y is going to be 1/2 that amount. And so we get something like 2.121. Before we can graph it, we need to figure out what the budget actually is that would remove the pain here. So how much does it cost to buy 4.243 x's and 2.121 y's? We plug it into our budget equation now. It'd be $1 for each of the x's, 4.243, plus $2 for each y, 2.121. And so our budget is going to be $8.49. Now let's go graph this information. I'll take a second and I'll graph the original and the final budget lines. You pause the video and do the same. And now let's graph that final budget line. So remember, the final budget line is going to involve a hypothetical budget of about $8.50 here. And so we take that and we say, well, if x's are $1, then we could afford about 8.5 x's with that money. And since y's are $2, we could afford about half of 8.5 x's. So let's draw this third budget line here. About 8.5 x's there. And half of 8.5 is about 4.25. And let's look at our solution again. It's 4.25 x's, roughly 2.12 y's. So there's our point C. Now notice the big difference between Hicks's illustration of income and substitution effects and Slutsky's. With Slutsky's, we saw that when we rotated this budget line, it actually rotated through point A, right? Because when it rotates through point A, that means that we're giving them enough money in this hypothetical situation so that they could buy basket A again if they wanted to. But with Sir John Hicks, instead, we're rotating it around the indifference curve. So this indifference curve for 9 utils here, the pink one, we're rotating it around the indifference curve to keep the utility the same. Slutsky, at point C, is getting more utility with that money. But in the Hicks case, we're getting the same amount of utility, but the person is not able to buy basket A with the budget in the decomposition basket, okay? And so in order to illustrate what's going on here with Hicks, we draw the same kind of diagram and we say when we're looking at good Y, since that's the one that the price changed, we started off buying 3 at point A, and then in the final basket we were buying 1.5 units of Y. But then in C, this point that is going to be in between 3 and 1.5 Y, we had 2.121. So 2.121 Ys. So that's our hypothetical basket in the Hicks scenario. In this case, what we see is that this point is a little bit closer to B, the final basket, than it is to the initial basket. So let's do the calculations here to see what those differences are. So 3 minus 2.121 says we have about 0.879 on this side. And which is that, the income or the substitution effect? Let's look at the budget lines. Between C and A, we are rotating the budget line, reflecting the change in prices, so that's reflecting the substitution effect. But between C and B, we're moving the budget lines parallel, reflecting a change in income. So between B and C, that is the income effect, and we see that that is 0.621. So using Sir John Hicks' method, we see that the income effect would be illustrated as being smaller than the substitution effect. So again, just visually comparing our little diagram here to what we got up here when we were looking at Slutsky. Now let's talk about compensating variation and equivalent variation briefly. Compensating variation asks, what is the minimum change in income that we need to get the person back to the old utility at the new prices? The logic here behind calling this compensating variation is we want to compensate the person for their change in utility. So we're asking, how much money would we have to give them to get them back to the old utility at the new prices? Compensate them so they're not worse off, they're not less happy. Sometimes we call this compensating variation the willingness to accept. In other words, what would be the minimum amount of money this person would be willing to accept in order for us raising the price on them? And all we're talking about here in this case is this hypothetical budget that would get them back to their old utility level at the new prices, minus what was their old income before the price changed. So we're just talking here about $8.49 minus their original budget of $6. And so, of course, that equals $2.49 would be the compensating variation. If we gave this person $2.49, they would not be mad about the price going up. They'd be compensated. Now, the equivalent variation. The equivalent variation asks a different question, but it's a different way of trying to measure the harm done for a price change or some other kind of change in the situation of a consumer. So the equivalent variation asks, what is the minimum change in income we would need to get in order to get this person to the new utility, the new lower utility in this example, at the old prices? And the logic here behind calling this equivalent variation is we want to know what loss of income would cause an equivalent amount of harm or an equivalent amount of pain to this consumer as the price change did. A way to think about this is we might go to a consumer and say, hey, the price of Y is getting ready to go up to 2. But we could stop it. We could prevent the price of Y from going up if you want us to. How much would you be willing to pay? What's the most you'd be willing to pay in order to prevent this rise in prices? So, in other words, how much money could we take from you, not raising the price, but cause an equivalent amount of pain or an equivalent utility change? So what we would want to set up here is we have to do another optimization problem. And the optimization problem, we're looking at the old prices here and the new lower utility. So we just set up equations that dictate that. So let's set those up. So the new utility is 4.5 utils here. So we want one equation to dictate that that is going to happen. So the x times the y, that's our utility function, has to be equal to 4.5. So we're going to put you at this lower utility level. We want to know how much money would be the cheapest way to get you there at the old prices. So the second equation guarantees that the slope of an indifference curve is equal to the slope of the budget line at the old prices. So we use the marginal rate of substitution, y over x, that's the slope of the indifference curves, and set that equal to the ratio of the prices before they changed, 1 over 1. Okay, so here we get y equals x, and we plug that in, and what we're going to end up with is either x squared equals 4.5 or y squared equals 4.5. Doesn't matter. So x squared equals 4.5, and what we're going to get is that x and y are going to be 2.12 units, square root of 4.5. And how much would this cost at the old prices? Well, it's going to cost us $1 for each x plus $1 for each y. And so that's going to cost us $4.24. So the equivalent variation compares their original budget, which was $6, to how much money would they need at the original prices to get that same utility as they would after the price change, $4.24, and that difference is going to be $1.76. Often we'll call this $1.76 either the equivalent variation or the maximum willingness to pay. And again, this is the willingness to pay to prevent the price change. Now we can also talk about the difference between gross substitutes and complements and net substitutes and complements. When we talk about gross substitutes or gross complements, here we're just saying overall, when you see a price change, what's the relationship between x and y? This is just what we talk about in a principles of microeconomics class. A substitute are two goods where when the price of one goes up, you buy more of the other. You substitute for the other good. So price of y goes up, you'd buy more x instead. And a gross complement would be two things that go together. So when the price of y goes up, you buy less y, but you also buy less x because you consume these two things together. So gross complements, gross substitutes just looks at the overall change that we would observe when a price changes. Now, with a Cobb-Douglas utility function, what we're going to find is that x and y are not gross substitutes, nor are they gross complements. When the price of y changes, what we actually observe is that the person does not change their purchases of x. So we see x equals 3, x equals 3 when the price of a related good changes. So they're neither gross complements nor gross substitutes in this case. Now, when we talk about net substitutes or net complements, what we're asking is, when we look at that substitution effect, what is that telling us? So if we're talking about x and y here, what we want to do is look at the difference between when the price of y changes, how much x do people buy? And so we could either look at the Slutsky version here and say that, well, when the price of y goes up, and we just look at the rotation here, right? The rotation is focusing on the substitution effect. We see that the person buys more x when the price of y goes up. Substitutes. Similarly, when we look at the Hicks decomposition here, when the price of y goes up, we see we're buying more x. Substitutes. Now, in any case that you have indifference curves with diminishing marginal rate of substitution, and you only have two goods, you must have that they are net substitutes. This is something that is just a mathematical law, that as long as your indifference curves are convex to the origin, they're steeper over here and they're flatter over on the right, diminishing marginal rate of substitution, and you're just analyzing two goods at a time, then the substitution effect has to imply that you're going to buy more x. There's just no way around that. Now, if you have three or more goods in a problem, anything can happen, all right? Last thing I want to mention here is when we're thinking about price indices, since we're talking about two different ways of looking at income and substitution effects, and we're getting two slightly different answers, and we're talking about compensating and equivalent variation, I just wanted to briefly mention the difference between a Laspeyres price index and a Paasche price index. These are two ways that we use to measure how much people are affected by price changes in the real world, right? The consumer price index, for example. Now, what the Laspeyres price index does is, well, let's look at what's similar between both of them. They both on the right-hand side are the same. So on the top of each of these ratios, we're looking at the new prices divided by the old prices. What distinguishes them is what's on the left side. What's happening to the quantities, in other words. So with the Laspeyres price index, what you're doing is you're asking the question, what's the cost to buy the old quantity of goods at the new prices on the top? So let's just calculate that real quickly. So on the top, we would say, well, the old quantity was 3 and 3 for X and Y, and the new prices were 1 and 2. So how much would it cost to buy the old quantity at the new prices? $9. We saw that $9 when we were looking at the Slutsky formulation for breaking apart income and substitution effects. Now, on the bottom here, we ask, how much did it cost to buy the old quantity at the old prices? Well, $6. That was just the original budget. And so what we get here is 1.5, which implies that it costs 50% more for the person to be able to get back to where they were. And where they were is in air quotes here. Where they were meaning buy the same things they used to buy. But we know that's not the truth, that when prices go up, even if we give them more income, they're going to substitute, right? So what this 50% more is doing, or this $9, or 9 minus 6, $3 is doing, is kind of overestimating the compensating variation. Remember that compensating variation we found was going to be $2.49. The Laspeyres price index overestimates that $2.49 that's needed to get the person back to the old utility at the new prices, and calling it $3, just the way that the Slutsky budget is $9, right? Saying that we would need $9 to be able to purchase the same stuff as before. The Laspeyres price index overestimates how much money people need to get back to where they were before, if what we mean by where they were before is at the old utility. The Paasche price index says, well, let's look at the ratio between how much it would cost to buy the new quantity at the new prices. So at the new prices, how much would it cost to buy what we actually buy? Okay, well, that's $6, right? Because in the real world, this person has $6 to spend, and we're assuming they spend it all. And on the bottom, we're asking, what would it cost to buy the new quantities of goods at the old prices? So we combine new quantities with old prices here. So we'd say, well, that's 3 times $1 is $3, plus 1.5 times $1 is $1.50. So we get $4.50. And in this case, that ratio is going to be 1.33333, or in other words, what this Paasche price index would be implying is that we need about 33% more to get back to where we were, depending on what you mean by where we were. The Paasche price index, that 33% increase, what it does is, let's compare that 33%, or 6 compared to 450, to the equivalent variation, right? So this is a $1.50 change in income that we're looking at in the Paasche price index, or a 33% difference in income. Our equivalent variation was $1.76. So while the Laspeyres price index overestimates, it would say we need $3 more to get back to where we were, the Laspeyres price index overestimates the compensating variation. What the Paasche price index does here, when it talks about the $1.50, it sort of underestimates the equivalent variation. So let's go back and look at that. $1.50, so that was the Paasche, and this is the Laspeyres. So it's an interesting relationship between what two different kinds of price indices tell us in relation to compensating variation and equivalent variation. So I know I've made this video far too long, as I usually do, but whenever I'm asked to address something, you know me, I want to go a bit into depth and tell you everything I know about the scenario. So I hope this has been informative so that you can understand what the difference between the Hicks income and substitution effects and the Slutsky is, the difference between compensating and equivalent variation, and as a free bonus, we looked at the difference between Laspeyres and Paasche price indices. As always, if you like this video, please give me a thumbs up. Please consider subscribing and tell all your friends. And if you disliked it, okay, give me that thumbs down as well. But please give me some comments about what you liked or what you didn't like, or if you have any questions, please, of course, let me know. This is Dr. Berkey signing out. And as always, I wish you the best of luck. I hope you learn a lot, and I hope you do well in all of your economic studies. Bye-bye.